Great question. This goes right to the heart of EV engineering challenges. Let's break it down. Traditional EVs mostly use radial flux motors, where the magnetic flux runs radially from the rotor center outward. In contrast, axial flux motors push flux along the axis of rotation, shorter magnetic path. The flux only crosses a thin axial air gap, which reduces losses. Disc-like geometry. A larger effective radius for the same motor size increases torque, since torque equals force times radius. High torque density. AFMs can deliver 30–50% higher torque power density compared to conventional radial flux designs. Thin and compact. Their pancake form factor makes packaging easier, ideal for in-wheel or space-limited EV applications. Example, companies like YASA, now part of Mercedes-Benz, and Magnax are pioneering AFMs that achieve high torque densities, greater than 15 nanometers per kilogram versus 5–7 nanometers per kilogram for conventional motors. A major issue with EV motors today is their reliance on neodymium and dysprosium magnets, which are geopolitically concentrated and environmentally costly to mine. Next-gen designs address this in several ways. Ferrite magnet, axial flux motors. By exploiting high efficiency and short flux paths, AFMs can compensate for ferrite magnets' lower flux density. This enables high performance without rare earths. Induction motors like early Tesla Model S rear motors use no permanent magnets, just copper rotors. Synchronous reluctance motors use rotor saliency, geometry-based magnetic reluctance to generate torque, permanent magnet-assisted. SynRM combines small amounts of ferrite or reduced rare earth magnets with reluctance torque for higher efficiency. Wound rotor motors. Instead of permanent magnets, use electromagnets powered via slip rings or contactless coupling. Allows tunable field strength with no rare earths. Hairpin windings and liquid cooling improve copper fill and heat removal, boosting current density without overheating. 3D printed rotors and stators may allow new magnetic circuit designs that use less material. Advanced steel laminations reduce core losses, enabling higher frequency operation with smaller motors. Higher power density leads to lighter motors, more range per battery kWh. Less reliance on rare earths means more stable supply chain, lower cost, more sustainable. Flexibility in design allows multiple motor topologies tailored to EV segments. In-wheel for city EVs, high-performance AFMs for sports EVs, SynRMs for mass-market vehicles. Bottom line, axial flux and other next-gen designs can achieve higher torque power density with fewer materials, and their geometry or reliance on reluctance torque allows either reduced or zero rare earth usage. This makes them strong candidates for the next generation of EV drivetrains. Would you like me to put together a comparative chart, axial flux versus radial flux versus reluctance motors, that engineers can use as a quick reference?